Okay, so last time, we got into kind of basically like stochastic optimal control. And in particular, the LQG problem, which is, basically the generalization of all this LQR stuff that we've already spent a lot of time on to the stochastic setting, where you have noise on both in the dynamics themselves, so the dynamics are stochastic, and noise on and you no longer have access to the full state. You've now got sensors that are only observing, say, pieces of the state or whatever, and those have noise on them too, right? So we've gone from like full state, everything clean and deterministic, to everything noisy. And so noise on everything, and you can't really ever have access to the full state. And last time we got through this whole thing about the separation principle and certainty equivalence. These are like really kind of bedrock classic results that should sort of stick in your brain. You should remember these things. These are super cool. And the fact that, even though those things don't hold in the general nonlinear case, we still do them all the time. And pretty much all like modern control things are kind of based on doing that separation thing into a state estimator and a controller. And theoretically, the justification comes from this LQR story that we just talked about. Let's see, what else to say about this? That sort of separation principle thing, there are RL methods now that try to not do that. And the gist there is, if anyone's familiar, right, there's a lot of like reinforcement learning methods that take as input some like big lagged history of observations instead of like just the current state. The reasoning behind that is that's trying to capture distribution information, and rather than force you to kind of like sum everything up into a single state vector. So it's maybe trying to like not do the separation principle thing to some degree. What else to say about this? The other thing I'll mention about LQG, LQG is like, again, one of these like great like theoretical playgrounds. So like control theorists love the LQG thing because it's simple enough that you can actually prove, theorems and prove results in that context, but like meaty enough that it actually means something and like is useful. And there's still lots of good work happening in this LQG framework. Last few years, some of my favorite work was Ben Recht, who's at Berkeley, and one of his PhD students, who's now a professor at Cornell, Sarah Dean, did a bunch of work showing, like, basically trying to answer the question about, like, like answer some deep theoretical questions about model-free versus model-based RL algorithms. And like the way they got at this was by doing it in the LQG setting, where you kind of can get some real answers. And they specifically looked at like this question of like, is it better to do something like policy gradient, where you directly optimize a feedback policy, or is it better to try to like learn a model first and then using the model do control, like model-based versus model-free RL? And specifically in that context, they were doing LQG. So we know the optimal policy is linear, so they just try to learn like a K matrix basically, versus should you learn the A and B matrices and then use those to just plug into Riccati and get the LQR policy? What do you guys think the answer to that is? Which one of those do you think is better? Because most of modern RL is doing more the policy gradient thing, right? Where you directly learn the feedback policy. It's in the general setting, it's like impossible to say anything about this. But if you try this specifically in the LQG setting, this is easy to try. You can just code these things up and do like, policy gradient or whatever, PPO, or, sort of system ID, and then like whatever. Anyone have any guess, like what you think would be the better thing? Specifically better in the sense of what's more sample efficient. So given the same everything, noisy observations, blah, 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 and you can try stuff and explore, should you fit the K matrix directly, or you should try to fit the A and B and then compute a K based on that? What do you think requires fewer samples? So so we got a couple different votes here. I mean, personally, if I were just going at this knowing nothing, I would guess that learning K is better because it's less to learn. It's literally just like the feedback matrix. Learning A and B, it's more stuff, right? Like A and B are bigger than just the K. But it turns out you're right. Learning, that's right. Yeah, yeah. So it's maybe task specific or something. So it turns out they're able to prove in this series of papers that, at least in the LQG setting, it is better to do model-based RL. It is more data efficient to learn A and B and then plug it into, DLQR or whatever, and to get the controller, than it is to directly try to learn the K matrix, which is kind of interesting. And like, to me, a little bit counterintuitive.
I mean, it's higher upfront costs, but better in the long
Yeah, I mean, it turns out it's just better, period. Like in terms of sample efficiency, basically, if you look at how much data you need to collect to get to some level of performance, in terms of cost or whatever, it's like strictly better to do the model-based version. I don't know, kind of interesting nugget, but this is like recent work in the last couple of years. That's, again, very current, very sort of in this RL kind of context, and it's basically built on LQG because that's the context in which you can actually get like hard results and like prove stuff, because the general nonlinear case is too hard for theory, right? Okay, cool. So that's just some random musings by me. That stuff's awesome, though. If you're interested, highly recommend checking those papers out. Today, we're going to kind of try to finish off this LQG story, specifically by talking about optimal estimation. So last time we basically made this argument that because of this separation principle stuff, the move is the optimal thing in this LQG setting is to basically just do LQR on your best estimate of the state, and that's optimal. So we already know how to do LQR. So now the story is how you actually get that best estimate of the state. So this is optimal estimation. And the answer is it's the Kalman filter, but there's a lot more to the story. So we're going to like kind of go through that today and maybe hit you to some things you might not have seen before in that context. Who's done a Kalman filter before? Like most of you guys, right? Who's seen it actually derived from scratch before and gone through that? Okay, so most of you guys, good. So we'll do that, and then I want to point out some interesting little, so we'll finish this LQG story, and then we're going to talk about duality. Who's seen this before? Like duality between estimation and control. A couple people. Yeah, so this is a really cool thing that will maybe bring us full circle back to a bunch of stuff we've already talked about in the class. Cool. So that's what we're doing today. Let's get into it. Okay, so first, from last time, I just want a quick summary recap of some things. First off, we did this whole certainty equivalence thing. Just, I kind of already just said these things, and the separation principle. And what all these things say is basically, at least in the LQG context, the best thing you can do is like, run some kind of state estimator to get an optimal state estimate. And then whatever that state is, you just plug it into the LQR controller, the optimal controller, and life is good. And so the idea here is in the stochastic setting, like you don't have to basically, like in the controller, you don't have to reason about the full probability distribution. You can just assume a deterministic optimal controller, and then you just separately design a state estimator, and you just hook them together, and that's optimal. Not true in general, but definitely true in the LQG setting. We proved it. But even though it's not true in general, we frequently do this in practice. Damn it. Even though it's suboptimal in general. And the kind of main whether you can get away with this or not thing comes down to what your distribution looks like over your states coming out of your estimator. And basically, you can get away with this as long as the distribution is unimodal. So like that peak of the distribution, in the unimodal thing is like a reasonable estimate for where you are. As soon as the distribution comes bimodal, like it's a bad situation, and you don't want to mess with that. Okay, so that's that. And so we started talking about this last time. Just to recap a little bit, and then before we get into the next thing, just kind of what we mean by optimal state estimation. And last time we talked briefly about this question of like, what are you optimizing? So this is the idea of like, I might have some probability distribution. It might be messy in general. And at the end of the day, to do this sort of separation certainty equivalence thing, I need a state to plug into my controller. So if I have some weird distribution that's like wiggly and weird and maybe multimodal and looks kind of like this, there's this question of like, what is the right optimal state to return given some weird distribution like this? And like we kind of talked about two options last time. One that's very reasonable is to pick the maximum of the distribution, the highest point on the distribution. So in this case, that would be up here probably. And this is called the map estimate or maximum a posteriori estimate. The other reasonable choice is to pick like the least squares answer or the minimum mean squared error answer, which is roughly speaking like the x that like is in the middle of the distribution, right? The average, the mean, right? And so that's maybe in this case somewhere over here, which you know is actually probably a pretty bad estimate because it's at a low probability, you know, point. And so we talked about maximum a posteriori or map. And like mathematically speaking, this is basically the argmax of the distribution. So this is in particular the posterior distribution. So we're going to get into this, but what this is the state conditioned on the measurements. So the measurements are y. So this is called the posterior. It's like after I've included all my measurement information, this is that posterior distribution that's been conditioned on all my measurements. So this is what I think the distribution over the state is given the measurements. And now I want to say, okay, what should I return? So one option is the peak. That's that guy. And this is probability of state given measurements. Okay, cool. And then the other one is this MMSE thing. Error, MMSE. And here, I actually want to belabor this one a bit because we're going to use a trick from this discussion. So this one is argmin over x hat, which is our estimate, like usually mean. And the thing we're minimizing is this expectation. So it's x minus x hat transpose times x minus x hat. So this is basically least squares or minimum variance, right? They're all kind of the same thing. Least squares or minimum variance. And now I want to show you a trick that I don't know. I know it only as the trace trick. That's what I call it. That's what I've heard people call it. I don't know if it has another name. If anyone's heard of this before, heard it under a different name, let me know. So the idea here is, and we're going to use this a bunch today, which is why I'm going to show it to you in this kind of simpler context. So, okay, so this is an inner product, right? It's a dot product between those two things. And the answer, the thing inside the expectation, there's a scalar, right? So I can, like, it means nothing, but I can wrap that scalar in a trace operator. And that's completely legal. It does nothing, right? The trace of a scalar is the same scalar. So I can just do that, and it's kind of trivial. So I'll go do that. So I can write it as this trace of x minus x hat transpose x minus x hat. Cool. So yeah, that was kind of dumb and did nothing for us, but here's the fun part. Okay, so inside of a trace, I can permute, like if I have a trace of a bunch of matrices like multiplied together, I can permute the entries inside the trace and I get the same answer. It doesn't change the results. Anyone heard of this before? So if I have like trace of ABC, it's the same thing as trace of like CA, blah, blah, blah. You can mix them around, right? So this is equal to, so I do that here. And that's not hard to show. So cool. So in that case, I'm allowed to do the following move and it doesn't change, anything. So I can do x minus x hat times x minus x hat transpose. All I did was reorder the product inside. And now instead of a dot product, this is an outer product, right? So it's trace of this outer product thing. What's that outer product thing though? We've seen that already. It's the covariance matrix, right? The expectation of that outer product thing is the covariance matrix. Exactly. So now what we have, and trace is linear operator, expectation is linear operator, so I can like flip these things around and it doesn't change the answer. So now I can kind of move this around a little bit, and this is now, I can move the trace outside the expectation because everything's linear. So now I can do trace of expectation of this outer product thing. And this outer producty thing is the covariance. So this is trace of covariance. Cool. Fun little trick. So this is just a trick that we should know about. We're going to use it today a bunch. Basically what it says is like least squares, where you're minimizing the squared error, where I take the inner product of the stuff. This is equivalent to minimizing the trace of the covariance under this kind of nice little trace trick. Fun fact, comes up, it's useful. Has anyone seen this before? A couple people? Okay, I don't know. I call this the trace trick. It's a fun little trick. It shows up in like particularly in Kalman filtery stuff, but it's kind of generally a useful thing to know about. It's a nice little math trick. And then the punchline here. So this is a thing we're going to use today a little bit. So there you go. And then the last note, which we said last time, is that this map estimator and the MMSE estimator, in the case of a Gaussian, what happens to them? They're the same, right? So if you have a symmetric distribution, like, unimodal, whatever, Gaussian, these things end up coinciding. And so we're going to also leverage that fact today and basically say we don't care which one we do. And it turns out in our derivation we're going to do today, you can get a Kalman filter from either perspective by solving either optimization problem. You get the same answer because they coincide. Today we're going to use the MMSE perspective to get the answer because it's more convenient for the way we're going to do it. But you can do this there are many, many routes to the Kalman filter. You can derive it a whole bunch of ways. I'm going to show you one way. There's at least 3 or 4 that I know of. My favorite one, which we're not doing a bunch, which is a bit of a bummer, is you can actually do it geometrically, which is super cool. If you haven't seen this before, the original Kalman paper from the 60s does it geometrically as like a bunch of projections. It's really cool. The original Kalman paper is awesome. You should check this out. The only other book I know that does it this way is the Kylith linear estimation book, which is a great book. I will give suggested reading at the end if you're into this stuff. I'm a nerd. I'm into these things. I like this stuff. But, if you're similarly, you should definitely check out the original Kalman paper in the Kylith linear estimation book. Okay, and then, yeah, okay, so, and then lastly, these are the same for a Gaussian. Okay, so that's a nice little kind of intro thing. And now what we're going to do is kind of leverage some of these little ideas, and we're going to go through a derivation for the Kalman filter, which is the optimal linear state estimator. So in this LQG context, you've got linear dynamics, Gaussian noise on everything. We're going to basically just go through and find the optimal state estimator. It is called the Kalman filter. You've all heard of this before. So let's do it. And like I said, even if you've seen this before, I think it's healthy because there's like, I know of at least 3 or 4 different ways to derive it. Like it's healthy to see it done a couple different ways and just kind of like wrestle with it a little bit. Okay, so the perspective we're going to go from today is recursive linear MMSE estimator. And so kind of what we're going to do today is that we're going to like play some tricks and shortcuts. We're going to basically assume out the gate that this thing is recursive, that it has a recursive structure, which we know it does. You can derive it without assuming that out the gate and come to that conclusion. We're just going to assume it out the gate. It's linear. We're going to assume that out the gate also, which makes things go quicker. And then we're going to go that MMSE route, which we just talked about. You can also go the map route and get the same answer. Okay, so the recursive means that we're going to maintain an estimate, and at each time step, we're going to update that estimate given a new measurement, as opposed to batch, which means taking a whole bunch of measurements at the same time and solving like for the whole trajectory at once. If that makes sense. Yeah, cool. So that's what recursive means. It means you update at every time step. Okay, so the general idea here is we're going to kind of bootstrap this we're going to assume a recursive structure. We're going to, oh yeah, that was awkward. Apologies. Assume an estimate of the state at like time k that includes all measurements up to the current time. So what that looks like, so our hat's going to mean estimate. And we're going to write this with a little shorthand. We're going to write it as k given k, or k conditioned on k. That's what that subscript means. And the longhand version of that is this is the expectation of xk conditioned on measurements from time step 1 up to k. Cool. So this is our estimate of x at time k, given all previous measurements up to and including the current time step. And so we're going to assume we have access to this at time k. And what we're going to basically do is assume there's a recursion. So given a new measurement at time k plus 1, we're going to figure out how to update this estimate to include that one new data point. And once we've done that, now you've bootstrapped this recursion, and you can do it for all time, right? That's kind of the strategy. And similarly, we're going to also assume we know the covariance on this state. The error covariance. Another way of saying this is we're assuming Gaussian beliefs over the state, right? So we just assume we know the Gaussian distribution on the state and that it's Gaussian and whatever. So this we're going to write as big sigma is going to be our state covariance. I'm trying to write this somewhat legibly. And same deal, we're going to write it like this k given k thing. And this is going to be the expectation of x minus x hat. So this is k given k. Outer product-y thing. Cool. So that's our shorthand. Basically, we're going to use these subscripts to indicate, the first one is the time step, and then the second one is what measurements they're conditioned on. And the reason we're going to do this is we're going to end up with kind of a two-phase update rule that's going to do a prediction step, which is going to predict x hat and sigma. So that's going to be like k plus 1 given k, right? So that's the next time step, but we haven't included the new measurement yet. And then we're going to do a measurement update step that's going to give us k plus 1 given k plus 1. So that's why that notation's there. Okay, so, right, so basically the game here is we want to figure out how to update x hat and sigma to include a new measurement at like tk plus 1 at the next time step. Cool. So basically, yeah, we're taking a lot of shortcuts. We're assuming linearity holds. We're assuming the Gaussian stays Gaussian. We're assuming we can do this recursively, right? All these things are true. I'm not going to prove any of those facts to you. I'm just going to like assume that structure going into it, and we're going to derive like the details. So basically, the move here is we can break this into two steps. And we're going to kind of go through and derive those two steps right now. Any questions so far? Yeah.
It's done after you discretize your system?
Yeah, all of this is in discrete time.
Do you have to discretize, then linearize, then do this? Or can you just assume the nonlinear system is linear?
I mean, it kind of doesn't matter what order you do that in. You can linearize in continuous time, then discretize it, or you can like discretize the nonlinear thing first and then linearize that. It doesn't really matter. You'll get basically the same answer. Yeah.
What circumstances were you interested in some conditional y to capital T?
Sorry, say again.
So what circumstances were you interested in raise the
xn, the whole, basically the entire trajectory conditioned on all the measurements. Yeah. Yeah. So that's like if you're doing this offline. If you're doing offline analysis and you have the entire data set and you want to then reconstruct the trajectory in an offline context, right? So then that's just batch least squares, actually. Then you're just solving a big batch least squares problem. The deal here that's slightly different. Another way of saying this is causal, as in the current estimate only depends on now and previous times, not on the future. The version you're talking about, the current estimate at some time in the middle of the trajectory would actually be informed by future measurements that I don't have yet, right? Which is fine if you're doing it offline and you're analyzing a data set offline. But if you're on the robot in real time, you can't use future measurements to figure out where you are now, right? So this is purely like a causal kind of thing where it's only taking into account past measurements that you have access to. Why do I care about the past measurements?
Yeah.
because they tell me where I am now. So here's like a simple example. Let's say I only have position measurements. My state, though, is position and velocity. How do I know my velocity if I only have a single position measurement from right now?
Oh, I see.
Does that make sense? So very, very frequently, this gets into this idea called observability, which is a dual notion to controllability. Usually the y is not, and one y at one time step is not enough to reconstruct the full state. Like very often it's some partial set of states or some, function of the state. For example, only the positions or something like this, right? Or only some part of the pose. It's not the full state vector. You can basically never get the full state vector kind of like in a clean way, right? So you're always trying to reconstruct that state vector from noisy partial observations. So in the context where you only have, say, positions but not velocities coming in from your sensors, the way you get velocity is by using previous positions, and effectively a naive way to do it would be to finite difference this position and your last position, right? But finite differencing amplifies noise and does bad things. So by doing a filter like this and leveraging the dynamics model, you can do much better than like naive finite differencing. Make sense? Cool. Anybody else? All right, here we go. Cool. All right. So here's what we're going to do. So the two steps. The first one is the prediction step. And the idea here is we're going to use our dynamics model, and we're just going to like propagate our distribution forward one time step. No measurements yet. It's just so the using our notation, this would be first we're going to predict the state estimate or the mean of the distribution. And this is going to be k plus 1 given measurements up to time k using our notation. And if I expand that out, it's by its definition, I literally just take the definition of that expectation and I plug the dynamics in. So this is the expectation of now just AXK plus BUK. And I remember I have my stochastic dynamics with the W in there now, plus WK, and all of this conditioned on measurements Y from 1 to K, right? So it's literally the definition of X hat K with the dynamics plugged in. And so if I stare at this for a second, like literally all that happens is I know U, it's not a random variable. The only random variable in there is the W. And remember, we're assuming it's zero mean Gaussian noise. So the expectation of W is 0. So all this does is essentially apply the dynamics to our last best estimate. So it just looks like this. AX hat K given K plus BUK. Okay, so that's the prediction step on the state. Now we also need to do the prediction on the covariance. So this is sigma K plus 1 given K. This is same idea. We're just going to take the definition and plug the dynamics in. It's plug and chug. It's not super hard. So remember the definition of this guy is X K plus 1 minus X hat K plus 1 given K. That's the outer product. And I'm going to start using shorthand notation here. So when it's, an inner or outer product and it's the same thing repeated, I'm going to do this. So I'll write the first half and then ... for the second half, save myself from lots of terribleness. Okay, so now same story. I'm just going to plug the dynamics in here. So this is expectation. And so now I'm going to plug the dynamics in on that XK plus 1 and on the X hat. And so I'm going to get the following. AXK plus BUK plus WK minus AX hat K plus 1 given K minus BUK and then ... same thing. Okay, so first thing to note is that the control term looks the same on all the X's and the X hat. So these go away. These cancel right out. That's not a random variable, blah, blah, blah. And then the next thing to note is basically the A's on the X's. Expectation's linear, so I can like kind of move some stuff around. And basically all that's going to happen is I can split this into two terms. The first one will have the X terms in it, and I can pull the A's out on that one. So that's going to look like this. So A, and then inside expectation of X K minus X hat K given K ... transpose, and then A transpose on the other side. And then the noise term the W shows up on both sides in this case. And so that's WK transpose, which is, all right, so then we've got these two terms. This one from our definitions is big W, the noise covariance, process noise covariance. And then the first one, what I've got there is just the original definition of sigma K given K. So this guy in the expectation is literally just the definition of the state covariance from the previous time step. So now if I like put all that together, I've got this like, I don't know, what I like to call matrix sandwich. And so if you think about this for a second, what this is saying is literally just, I take the covariance at time K and just shove it through the dynamics. That's what that sandwich with A is. Yeah.
Don't you have cross terms as well? Like the X terms times the W terms from the other way.
Yeah. Oh, yeah. Sorry. This is a thing we talked about a bunch last time, which is this idea of the noise at time K is uncorrelated from the state at time K. So the idea here is if I'm at time step K and I have a state, whatever it is, cool, that's where I am. The noise sample is coming in after that. It's coming in the time, in the dynamics that are propagating me to the next time step. And it's assumed to be drawn from a Gaussian at that time, right? So the current state does not depend on, basically, it's sort of weird, ambiguous because of the way we're defining this in discrete time, but essentially that noise is drawn at time K once I'm already there. So these things are not correlated. Yeah, so I should write that again. We did talk about this last time, but yeah, thanks for the reminder. So we're saying that basically XK and WK are uncorrelated. And therefore the cross terms are zero, right? By definition. Is everyone cool with that? Yeah.
How did you go from K plus 1 conditioned on K to just XK? From one step to the next.
Sorry, yeah. So A times, that's probably just a mistake. Okay, so yeah, sorry. This one, to be clear, this one, this is correct. And what I'm doing is writing this as A times XK. This one is A times XK given K. This is wrong here. Oh, so let me fix that. Thanks, good catch. So all we're doing is putting in the dynamics, right? And writing it as the last time step fast forwarded by the dynamics. And basically at the end, what you get is this thing, which is saying, I just take my covariance at time K and run it through the dynamics. And then I add on a process noise term that's just making the noise bigger, right? Okay. Everyone cool with that? Or if we're going fast. And that matrix sandwich thing shows up all the time. That's literally just how I propagate like a covariance matrix through a linear transformation, right? It's like a change of coordinates on a matrix or whatever. So that shows up all the time. And it falls out here from doing this expectation math, but just generally, if you have a matrix written in like one coordinate system and you have a linear change of coordinates, like you kind of smush it on both sides, right? And that's how it works. Okay, so that's the state and covariance prediction. So now I have from this, if I have a Gaussian at time K, given all my measurements so far, I can predict where I think the state's going to be at time K plus 1 and the covariance by running it through this, right? So it's just run the state, the mean through the dynamics, and then the covariance basically run through the dynamics and add a process noise term to like inflate it a little bit. Okay, so that's that. The next step is the measurement update. Okay, and so the idea here is we're gonna like define a couple things and take some shortcuts. Basically, I'm gonna assume a linear update, blah, 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 and then we're gonna figure out the details. So right out the gate, I wanna define this thing called the innovation. Has anyone heard of this before? Okay, so this is like a common lingo in like the filtering literature. I'll write down real quick. So we're going to use the letter Z for this. And I guess this is at time K plus 1. And what this thing is basically the difference between the actual measurement. So the y here is the actual measurement you get at time k plus 1 and the predicted measurement. So I take my predicted state and I run it through my measurement model. So remember here, I'm assuming my measurement is c times x plus a measurement noise term. So the predicted measurement is just this guy on my predicted state. So this is k plus 1 given k. So in some sense, this is like your surprise. I actually think the word I would use for this is surprise. It's like how off your prediction is from what you actually saw, right? So this, I mean, people call this innovation. It's basically, the idea is it's the error in your prediction, so to speak, right? It's the how surprised you were by the measurement you got. And the reason we bother with this is basically the error that you feed back in the Kalman filter, right? So the Kalman filter is linear feedback on some kind of error, right? To try to control. One way to think about it is it's trying to control your state estimate, and it's doing that by feedback on the measurements. And this is the thing that's actually getting fed back. This is the error term you've got. It's the error between your predicted measurement and the real measurement that you actually got. Cool. Cool. So if we write this out, kind of like in some more detail, like what this thing is, it's so the y there is going to be c times the actual, say, state maybe, plus this measurement noise term we talked about before, and then minus this like expected measurement. Cool. So that's like the definition of that thing. And then the next thing we need, unsurprisingly, is the innovation covariance. So I need to figure out what the covariance of z is going to be. This thing's Gaussian, right? So Gaussians, we kind of assume this here, but like if anyone hasn't heard this before, Gaussians stay Gaussian under linear or affine transformations, which is kind of what makes all this derivation work. So if I take a Gaussian and plop it through linear dynamics or a linear measurement model, it stays Gaussian. Yeah.
Is the C matrix given or?
Yeah. So C is our measurement model. It's the we're assuming it's linear, and it's basically if I have the state x, it's the function that maps x into my measurements.
And it doesn't update through time.
It can, yeah. So I should have said this out front too. So here we're assuming the standard like LQG assumptions from last time. So it's xk plus 1 equals a times xk plus b times uk, and then y equals c times xk. So that's it, plus noise on everything. And here we're going to write everything as LTI. So the A and the B and the C don't change in time. Nothing changes if they are time varying, though. You can like carry through the entire thing with indices on the C's and A's and B's, and it all still works the same way. I'm not going to do it here just to save myself writing and like little subscripts that you can't read anyway because my handwriting's bad. But does it make sense? All right. Everyone cool? Yeah.
Why are we passing the actual through the measurement model? We only have that directly, so
You're not passing the measurement through the measurement model. You're passing the state through the measurement model.
why are we why do we need to do that? Why can't we directly take that as say y hat?
It's not y hat, it's just y. That's a thing you get from your sensors. There's no.
The c x hat will be, we can take that as y hat and subtract that, and that will be the difference between the actual measurement and the.
Sure. If you want to call that thing y hat, that's fine by me. The reason we're doing it this way is because I'm going to use this in 1 second to like derive this covariance result. So yeah, bear with me for 1 sec. All right, so the next move here is we're going to look for this innovation covariance. This actually is quite useful in filters in general. We're going to call this S k plus 1, and this is going to be expectation of z transpose, like, just how we're used to thinking about covariances. And so I'm going to expand this out and plug the definition of zk plus 1 just there in. So it is c times xk plus 1 plus vk plus 1 minus c times x hat k plus 1 given k times that transpose. And now we're going to play our game of things being uncorrelated and say, same as before, that like vk plus 1 and x k plus 1 are uncorrelated, which is sort of obviously true in this case. This is saying the state at the current time and the sensor noise are uncorrelated. This is definitely not true of in general, right? Like this could be, you could imagine a scenario in which your state is correlated with your measurement noise. This is not that hard to cook up. For instance, like let's say you have a sensor where the noise is proportional to the temperature, or if you have a camera and like it's proportional to like just the ambient light, so you could very much imagine scenarios where like your robot pose influences the amount of noise you get, right? Like if I'm in a very noisy environment versus a less noisy environment, if like I don't know, IMUs are actually generally the noise is proportional to temperatures for, so if I'm in a hot room versus a cold room, if I move around, you could have this one is, you could imagine scenarios which is not true, right? And there's ways to deal with that, but here we're going to make the standard assumption that they're uncorrelated. The idea there, right, like wherever I am right now, I'm just drawing a random sample from a Gaussian right now on my sensor effectively, and that's what this is. Cool. Okay, so we're going to assume that uncorrelated thing again. And now kind of expand this out. So this is SK plus 1 is, and so similar game as last time. I'm going to pull the C's out here and split this up into two terms. So I'll have one term that's just the X stuff. So this ends up being XK plus 1 minus X hat K plus 1 given K, dot, dot, dot. And then C transpose on the other side. And then we're going to get a noise term. It's going to look like this. And so this is like, if you stare at this for a sec, it's pretty clear that this thing in here is something we've already derived, which is the predicted state covariance. So K plus 1 given K from the last step. And then this guy is just the sensor noise covariance. And so then the punchline from this is that this innovation covariance is basically smushing my predicted state covariance through the measurement model. So it looks like this. And then plus the measurement noise covariance. Make sense? Cool. And then, yeah, the reason we care about this is the innovation is the error signal that we feed back into the estimator. And this idea of like innovation covariance, one area this is like really useful in practical filter design is this is a really, really good way to do outlier rejection. So you basically remember like innovation is surprise, and I have a covariance on my surprise. So this is saying like if I get a measurement that's like three sigma away from my prediction, or like more than that, say it's like 5 or 6 sigma way out, the odds of that being legit are pretty low, right? And so the maybe most standard way to do outlier rejection in a filter is to look at this innovation and this innovation covariance. And if your innovation is huge, like relative to the covariance, if it's like many sigma away, like you put some bound on that and you throw it out if it's more than say 3 sigma away from what you expected, and you call it an outlier. So I don't know, fun fact, these are useful things. All right, cool. So that is the innovation. And so now that we've got this stuff defined, here's, and just that statement I just made, we can now, write down what the state update is, the measurement update based on those things, just basically this and the fact that it's linear. It's just doing linear feedback on that innovation. So here's what that looks like. We've got X hat K plus 1 given K plus 1. So like our updated estimate is going to be the predicted one. So K plus 1 given K. And then plus this feedback term. We're going to call the feedback gain matrix here L instead of K, because we're using K for LQR, and we will mix these together. That said, L actually has historical precedent and is not uncommon. L is for Leuenberger, who is another giant of, kind of linear dynamical systems theory, who was the first guy to really like formulate state estimators in kind of state space this way. So this is LK plus 1 times ZK plus 1. So, and this L here, in our context, you can write down any L you want. If you just write a random one down, like if you do old school pull placement kind of stuff and you're not optimizing it per se, it's called a Leuenberger observer. Just like you can have any kind of linear feedback that's not LQR, right? If you optimize it and pick the optimal one in the sense we're about to do, then it's called the Kalman gain. And this is now a Kalman filter. So this L is going to be called the Kalman gain. Okay, so now we know how to do the state update. The big question is, what's that L supposed to be? And we haven't gotten there yet. We're going to assume it looks like this. It's linear feedback on the innovation. But we need to do a little bit more to get to the actual expression for L. So the first step in getting there is now we're actually going to write down the covariance update. Because remember, we also need to figure out what sigma k plus 1 given k plus 1 is. So to get to this, we're just going to go back to the definition and plug stuff in. So this is x k plus 1 minus x hat k plus 1 times that transposed. So now what I'm going to do is just go plug in basically this state update equation and expand it out. So here that looks like expectation of x k plus 1 minus x hat k plus 1 given k minus L k plus 1 times, and now I'm going to plug in the definition of Z. It's just plugging in all stuff we've already done. It's slightly messy. C times x k plus 1 plus v k plus 1 minus c times x hat k plus 1 given k. Okay, so that's 1, 2 parentheses, and then same thing over here. Transpose. Okay, so I just plugged in the update equation right there, and then I plugged in the definition of Z from up above in this whole thing. So now there's like another round of this whole assuming things are uncorrelated. Once again, it's VK plus 1 and XK plus 1 are uncorrelated, which we already kind of did. And then we're just going to expand this thing out a little bit and massage it. It's not hard. It's like obvious stuff based on like if you followed all the rest. And so what this works out to be is I minus LC times sigma k plus 1 given k times I minus LC transpose. So it's the matrix sandwich of like our predicted covariance with this sort of Kalman gain thing. And then the measurement noise similarly sandwiched through the Kalman gain. Okay, so this is the covariance update equation. Has anyone seen this thing before in their Kalman filter explorations? Yes, kind of maybe. So we had a little sidebar discussion a couple classes ago with some folks who were messing around with like the ILQR stuff and talked about how you remember we went through the LQR derivation a few different ways and in fact came up with different expressions for the Riccati equation a couple different ways. Same thing is true in Kalman filter land. This form of the measurement update has a name. This is called the Joseph form. Fun fact. And basically, I'm showing you this one. This is the one you should actually use in practice. There's at least 2 or 3 other ways to write this that all have various shortcomings, numerically speaking. They're all exactly identical in an infinite precision arithmetic. But this one is the one that's nicest in a computer and with floating point because it's symmetric. So like both these expressions are symmetric. So the answer is going to be a symmetric matrix. And because I'm adding these 2 terms together. So other versions of this are not symmetric as they're written. And so because of floating point roundoff, they can give you not symmetric covariances, which is bad. And then also a lot of them have minus signs in them. And under floating point roundoff, that can give you an indefinite, i.e. a covariance with negative eigenvalues, which is also a big no-no. Like covariances have to be at least positive to semi-definite. So this one is basically guaranteed to give you a symmetric positive semi-definite matrix by construction because of the way it's written. So you should do this one essentially. And if you see other ones written down in books and papers, which you will, that's fine. But when you go code up your Kalman filter, you should do it this way. There's other ways to write this too that are kind of okay too. There's other, but this is like kind of the ones you will see, probably the best one. Yeah.
Tangential, but is there like a survey paper that goes through all the lessons learned as far as really like as far as floating point precision, like the limitations of hardware?
Yeah.
It's like those things are hard to quantify.
Yeah.
That quantification, but then when you look out, it's like, oh man, it's made a big difference.
Yeah. I mean, there's almost certainly papers that kind of go through this stuff. I would say the stuff that I'm talking about now, these are like street fighting, kind of skills that are like more tips and tricks and like practical things that are not so much theory or math or academic.
So nobody's written it down.
I mean, there's definitely some of this stuff written down, but these are more like the hard won lessons of like, if you like go talk to people who've written like these things on real deployed systems and like gone through the pain, like these are the things you pick up doing that, so these are, I'm telling you these things, but like a lot of this stuff is just like kind of street knowledge that's not like written in books and papers. Some of it you'll definitely find, but like I would say there's a whole bunch of like these kind of street fighting tricks that are not sort of common knowledge in books and stuff. So I'm feeding you some of them. I'm happy. There's specifically for Kalman filters, there's this guy, Tucker McClure, who who's a consultant on this kind of stuff, who has an awesome series of blog posts. His website is anuncommonlab.com. If you go plug that in, and he has a really, really awesome like 3-part blog post series on like a lot of practical tips and tricks for Kalman filters that like are he basically does Kalman filters for a living as a consultant and like has done lots of this, and he has like a whole really great, like actually his blog post is one of the best resources I know of for this kind of stuff. So that's where I would look. If you want me to, I'll send it out on Piazza later. You already got it. Yeah. Send it out to your friends. It's good. It's really good. Yeah. Cool. All right. Yeah.
Happens like state space is like y equals cx plus du. What if you have a d term?
Yeah.
If you're in controls at all.
You can do it that way. Like practically speaking, I've literally never encountered a system where that was a thing. So that's why I don't do it. But yeah, it doesn't change the derivation much. Cool. It basically shows up like the BU, where it shows up in the mean, but not the covariance update. It doesn't really do much. It like if you followed this, if you want to throw the DU in there, it's like no big deal. And you can find that stuff in books and stuff too. Okay, so that's the covariance update. That's the Joseph form thing. That's the street fighting skills about covariances being positive and definite and symmetric and stuff that you should know about. The other way to fix that, which is the legit thing, and the Tucker McClure blog goes into this, the legit way to do this on an embedded system, if you really want to make a bulletproof real deal Kalman filter, is to write it in the so-called square root form. So what that is rather than keep track of sigma in the filter, you keep track of the square root of sigma, aka the Cholesky factor. And the reason you do that is then if you keep track of the Cholesky factor, the actual covariance is always the square of that thing. And so if you square that matrix, it's guaranteed to be symmetric positive definite. So that's a slick trick that guarantees positive definiteness under like floating point round-off error and stuff. It's more numerically stable also and has other nice numerical conditioning wins. The blog post has all that stuff. It's great. There's a like awesome, I'm getting really sidetracked now, but like historical anecdote. The Kalman filter, this is obviously Rudy Kalman in the early 60s. The extended Kalman filter is sometimes called the Kalman-Bucy filter. Kalman-Schmidt filter. Schmidt is the name on that. Basically, the story there is in the Apollo program, this was only like a few years after the original Kalman paper. I think it was in like 1967. Schmidt was an engineer working at NASA Ames, I think, on the guidance, like navigation for Apollo. And basically they had this like intractable problem of like how to navigate Apollo. And he basically went home over the weekend. The legend is he basically went home over the weekend, saw the Kalman paper, which had like just come out like fairly recently. And this is pre-internet. So like, whatever. He came across the Kalman paper, original one, like had the aha moment, invented the extended version, like the nonlinear version for the Apollo like navigation problem, and like showed up at work on Monday with the answer. And they flew it. That's how they flew to the moon. It's kind of an insane, legendary, kind of story. Anyway, cool. So Kalman Schmidt All right, so okay, we got to finish. Kalman gain. So this is now how you find the L. Okay, so basically what we're going to do is we're going to use this MMSE idea. So what this means mathematically is we're going to minimize the essentially this like the least squares thing, right? So it's expectation of the inner product of these things. And now we know how to get all this stuff. So it's this inner product. And the next move is we learned the trace trick at the beginning of today. So this is equal to the trace of our covariance, our updated covariance, k plus 1 given k plus 1. So this is the thing we're trying to minimize. And specifically, we're trying to minimize that trace of that covariance as a function of L, which is literally this Joseph form expression right here. So literally what we're going to do is try to minimize the trace of this guy as a function of this guy. That's what we're doing. So quick question, what kind of function is that as a function of L? It's quadratic. Yeah, it's a quadratic function of L. And if you stare at this for a sec, you know, sigma's symmetric positive definite. So it's a convex quadratic function of L. So that's beautiful. We know what to do with that. So the answer is I basically take this expression and I take its derivative with respect to L and set it equal to 0. That's the whole game. And that gives me the Kalman gain. So let's write that down. I'm going to skip the details because the details are messy, because what I'm actually doing here is I'm differentiating a matrix valued expression with respect to another matrix. Technically, that derivative is a fourth rank tensor, which is super, super gnarly. You can do it. You can actually do it with specifically with the Cron-Vectrix that we talked about when we did DDP. So the legit way to get this is to use the Cron-Vectrix to massage this around into the, or you can write down the tensor. It's a little messy. So I'm going to kind of skip those gory details and just tell you the answer. If you want the gory details, you can try doing the Cron-Vex stuff on this. So what we're going to do is set partial of trace of sigma k plus 1 given k plus 1, which again is just up here, this Joseph form expression, with respect to L k plus 1. We're going to just take that derivative and set equal to 0, and then solve the resulting thing for L k plus 1. So if I do that, the answer that you find is L k plus 1 is sigma k plus 1 given k times C transpose times S k plus 1 inverse, where that's our like innovation covariance thing that we just derived. So that's the punchline. It's a little messy to get there, but it's not really that bad. And I'm going to like sort of save you the pain right now because it's not very interesting, just a lot of algebra, and tell you the answer. It wouldn't hurt you to like go actually do this yourself, just to like, by the way, yeah, if you actually want to know this stuff, I like highly, highly recommend like what I would suggest doing if you really want to learn this stuff, which I like still do occasionally, is like start from scratch and say, okay, Gaussians and linear dynamics and linear measurement model, and just start from there and then try to derive this whole thing, which I can still, I like basically once a year, I try to just do this to make sure I like stay sharp and still remember how. But like doing that kind of stuff, like deriving LQR from like the basic building blocks, you know, once in a while, like that's like what you should be able to do if you really want to understand this stuff. Okay, so to summarize the whole thing, so first off, we're going to start with our kind of Gaussian prior. So in this case, this would be like x hat at time 0, you know, and similarly sigma at time 0. And then obviously our system specifications like ABC and the noise covariances, all that good stuff. Cool. So we start there. Then we're going to do the prediction step, which we saw is, you know, basically shove the mean through the linear dynamics. And similarly, shove the covariance through the dynamics, where you get the matrix sandwich deal. And then the noise added on. Next, you calculate the innovation stuff. So innovation and innovation covariance, which looks like this. So basically, remember the definition here is surprise. There's a difference between the measurement we actually got versus the measurement we predicted based on our predicted state and our measurement model. So surprise, and I really should I just want to change the name on this. I think innovation's a weird, surprise is a way better name for this. So and then the covariance on that guy, which similarly, right, we take our predicted state covariance and shove it through the measurement model. And then tack on the measurement noise covariance. So there, then we're going to calculate our Kalman gain. So that's just what we just got. Sort of k plus 1 given k times c transpose times s inverse. And then finally, we're going to do our measurement update. So that looks like this. So it's linear feedback, like we said, on the innovation. And then we do the sigma update, which is this Joseph form deal, which you may see other versions, but those other versions are not as good. You should do it this way. Sigma k k minus L C transpose, and then noise term. Okay, cool. So that's the whole thing. And then finally, you just repeat this, right? Now we've bootstrapped the recursion, and you go back to step 2, keep going. So that's the recursive thing, right? Okay. Now we're going to show you like the example code. Anyone have questions on this while I get the code up? Yeah.
Yeah, you said x hat of k was dependent on the whole measurement vector, but didn't you just kind of show that it's like dependent on your measurement vector, your measurement at that time, and then your last state?
Well, yeah. So I mean, you have a state at time k, you predict the time k plus 1, take a measurement, and like you fuse those together. Yeah.
Like the expectation, page back, sorry. Like the expectation is the state given your measurements from 1 to k.
Yes.
So it seemed like slightly contradictory.
Sorry. Yeah. Explain.
So
you're saying it only depends on the measurement at time k plus 1, say, and not the previous ones. So it depends on the previous ones by virtue of them being folded into the previous states.
Okay.
Right. So at time k, if I've run this thing for k time steps, I have already done k measurement updates on all those previous measurements, right?
okay.
So the idea is basically at each time step, I'm including one new measurement, but I'm doing that on that previous state estimate that has already had the previous measurement and then the one before that folded into it, right? Does that make sense?
Yeah.
So what this is a really, if you know linear least squares, if anyone heard of recursive least squares, this is basically a really fancy version of recursive least squares, which if you know linear least squares, right, like ax equals b or ax minus b, right, minimize sum of squared errors. If you stare at that problem, you can derive a recursion there where you basically can update the least squares estimate one row at a time. So like the idea there is if I do solve a least squares problem for ax and b, if I add one new measurement, so I like one new row to a and one new row to b, it turns out I can efficiently update my previous least squares estimate by just like solving one little problem given that one new row instead of like having to resolve the entire least squares problem. So that's called recursive least squares. That's a nice simple idea that's like fairly easy to grok that you can find on Wikipedia and stuff. Basically, this whole Kalman filter thing is a very fancied up version of that, where you've got like dynamics models and stuff like that. I don't know if that helped at all. Yeah.
At what point can you like or like, I don't know if it's cost saving, but forget previous measurements if you don't need them anymore.
Yeah, so the idea of this recursive thing is there's no cost. You don't need to forget. Like here, right? Like basically the algorithm at each time step, it's the same thing. I do this measurement update on this one measurement, and the measurement at each time step. So you're totally, if you were doing a batch kind of thing where I was trying to like, that's the beauty of this recursive idea. If I were solving that, going back to the least squares example, if every time I got one new measurement, I had to stack all those up and solve a giant problem, you're right. You would want to like forget and maintain a fixed horizon there or something. But in this context, it doesn't change the expense of the update at all. Like every update, just a single measurement. I just do it at every time step. That never changes. And like, I'm basically folding in all the prior information into that Gaussian at every time step, right? So that the cool part is the complexity algorithm is independent of the horizon length. So you don't need to forget, basically. If you want to forget, you can. There's actually pretty straightforward ways of introducing what's called a forgetting factor here to do that kind of thing, but you really don't need to. By the way, that those forgetting factor ideas are all basically also just very closely related to the covariances in here. So you can kind of tune the covariances in such a way that it kind of gets you that effect. Basically, high process noise is very similar to a forgetting factor. It's saying I don't trust the propagation very much. So it'll kind of like downweight the predictions and upweight the newer measurements. Okay, so just to kind of run us through this real quick, this will be posted. This is like a very, very, very simple implementation of this thing on a very dumb system. This is a double integrator, so like the sliding brick in 1D, which we've seen many times. I'm putting noise. I'm basically having some kind of, white noise drive signal to this. So it's like basically a random walk. And then I've got white noise on the position measurements. And I'm assuming just position measurements, no velocity measurements. So that's A, B, and C over there. Just set up stuff. I'm going to put an LQR controller on here that's trying to drive us to the origin. So we're going to do the whole closed loop LQG thing where I hook up the Kalman filter to the LQR controller. This is like, very straightforward, dumb, like LQR cost. I'm going to get out my LQR controller. I'm going to start this like, I don't know, a meter to the right, say at 0 velocity, and the controller is trying to drive it to the origin. And I'm going to initialize the filter with like a very bad initial guess, which is the things at the origin, which is wrong. And then like an identity covariance, just random stuff. This is just kicking stuff off. And then down here, here's the, I wrote out the first time step in detail here. So you can see like, this is literally just the stuff we just wrote down, all the steps. And then you can see like in the propagation, I'm actually like I'm drawing a sample from a Gaussian here and adding that on to the dynamics. That's the stochastic dynamics. And then we're just going to kind of loop this and see what it looks like. So you can see basically the blue here is ground truth. And then the orange is the estimate. So it's like, I put a lot of noise on here. So it's quite noisy, but you can see that the estimate is tracking the truth, right? It's a noisy version of it. We can run this a bunch. I'm being pretty mean here and putting a lot of noise. So it's like kind of, obviously noisy, but the punchline is this actually does, work and still like in spite of the noise, right? It's like the mean is converging to the origin, and you can run this a bunch. You guys can try this. One thing I did want to point out that's kind of fun is if I plot the covariance entries, what's happening? This would show up, by the way, if I plot the Kalman gain, what's happening? Well, they're obviously getting smaller, which they should, but in particular, they're converging towards steady state values. That is neat. Where have we seen this before? Infinite horizon LQR. Yeah. So basically, because this is an LTI system, similar in the LQR context, it turns out there's this duality thing, which we're going to talk about in 1 second, but like similar to the infinite horizon LQR thing, here, the covariance on the state and the Kalman gain all converge to steady state values after a while in the LTI context. So if everything's time invariant, like the covariances are time invariant, blah, 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 it converges to a steady state value. And in fact, you can play the same game here. If you really have an LTI system, you can basically just do this and then you can basically just run with a constant Kalman gain that is the converged steady state value, very similar to the LQR thing we talked about.
Converging to 0?
No, this is non-zero. I mean, it's just a lot smaller than we started with because I started with a really bad initial estimate. Point is, after you run this for a while, essentially you're going to converge to some steady state covariance, which is the best you can do. And like, because you're constantly, basically, one way to think about this is the filter is trying to squish the covariance down as aggressively as possible. But the system dynamics, right, at each time step, remember, we're adding process and measurement noise to it. So one way to think about this is the filter is trying to squish the covariance and the physics is trying to blow it back up. And so those things are fighting each other. And if you run this long enough to steady state, they're going to kind of reach an equilibrium and you get this steady state covariance value. That's in the time invariant case, but in the general case, you know, it can wiggle around and do whatever. So if it's time varying or nonlinear, it'll do weird stuff. In the LTI case, though, you get this kind of steady state thing that's very reminiscent of what we saw with LQR. And the last thing to talk about is kind of closing that. So yeah, this will be posted. You guys can check this out. Is kind of connecting the dots on that duality story a little bit. So just a couple closing notes. First one is, what happens if your stuff's nonlinear? So how do we apply this to nonlinear systems? And, you know, you guys have probably seen this stuff before and probably implemented stuff like this before. So the first thing to do is what's called the extended Kalman filter, right? Where you basically just linearize at each time step about your current estimate. And that's it. And proceed. And you know, this has many issues. And if anyone's ever done one of these, right, it's very finicky, it requires tuning, but this does work. And it, you know, goes back to Apollo, it's how they flew to the moon. But there's lots and lots of, you know, this can be quite finicky in a lot of scenarios. And so there's many other generalizations to the nonlinear setting that many of which you probably heard of, right? So there's all kinds of variations on the EKF, there's iterated EKFs, and then there's the unscented Kalman filter, right? There's various other sample-based versions of this idea. And then you can get into like particle filters, right? That are like kind of Monte Carlo sampling versions of this idea. So it's lots of versions. Cool. Okay. And so now the last topic, which is really cool, is this duality idea. So what I'm going to show you right now is how not even just the linear case, but the general nonlinear case of this MMSE estimator is actually exactly equivalent to an optimal control problem, which is kind of cool. And so if you can do that, then it sort of follows that in the linear case, there's some connection to LQR. So here's what this looks like. This MMSE problem is equivalent to the following optimal control problem. So I'm going to kind of do my usual thing. And what you'll see is, so we're going to minimize over a state trajectory, and we're going to also minimize over a noise trajectory. So it turns out the process noise, the W's, take on the same role as the control inputs, which is kind of funky. Here's how this looks. So my cost function is going to look not that different than what we're used to seeing. I guess maybe I'll just make this. So it's going to look like, here's our measurements, our Y's, and this is our measurement model. So this is general nonlinear measurement models. We'll call that G. And then we've got a quadratic cost, well, quadratic-ish, that looks like the following thing. Let's write it down, then maybe talk about it. And then we've got a sort of what would be our control cost, but here it's the process noise. And that looks like this. And then we've got our dynamics constraints, and those look like this. All right, so let's talk about what this all is. So this is your measurement model. And this is basically, this whole term is your state cost. And in the case that your measurement model is linear, this is a quadratic cost on the states, right? So that G turns into C times X. And if you kind of expand that out, it just becomes a quadratic cost. And then this is basically like your sort of control cost. So, right, it looks just like U transpose R of U. And then the W's here, which are the process noise at each time step, these become your controls. And what you're weighting up there, the weight matrices, right? So the equivalent of Q and R from LQR are V inverse and W inverse. It's the inverse noise covariances. If anyone's looked at a log likelihood function before, this should look very familiar, right? So basically the cost, the quadratic cost in here is the log likelihood of a Gaussian. That's the way to think about it. Like this quadratic thing is exactly what shows up in the exponent of the definition of a Gaussian distribution, right? It's like X minus mu times inverse covariance times X minus mu. Remember from when we wrote that down. Okay. Okay, so some notes on this. If f of x equals a times x and g of x equals c times x, this whole thing is an LQR problem. And if you do that, you can like go solve that LQR problem with dynamic programming like we know how, and you'll basically get a Kalman filter, but it'll be this weird, you know, like it basically that's how you show this kind of weird equivalence, this duality between the Kalman filter and LQR is via this definition. But the kind of, you know, interesting thing is this is general. This sort of correspondence holds up in nonlinear settings too. So nonlinear F, nonlinear G, it's still, there's still this duality. Basically, I can write down a control problem that is exactly equivalent to the state estimation problem. The cool thing now is this opens us up algorithmically to doing a lot of interesting things and like to other weirder generalizations of Kalman filters for nonlinear problems. Like if I were to go solve this problem in like an MPC style way, this is a thing people do. This is called a receding horizon state estimator, or backward smoothing extended Kalman filter sometimes. The idea is like I'm basically solving a full nonlinear least squares problem over some window into the past. So instead of MPC looking forward over a second or two, this is me looking backward over a second or two of previous measurement history. And so that I'm solving as a nonlinear least squares problem. And then the tail, just like in LQR, I maintain a cost to go approximation to extend me into the future past where I'm optimizing my optimizer horizon. In this context, what I'm doing is the tail is represented by a Gaussian prior. Basically, like for anything that's older than my batch history in here in my horizon, I represent as a Gaussian, like a la EKF, but I keep the nonlinearity in some window and solve that full problem. So there's lots of cool things you can do with this. It's kind of cool. So this is like the big idea around duality is that there's like an equivalent control problem for the state estimation problem. And with that, we are done. Thanks, guys.